Welcome to today's paper reading. Today's paper is titled, A Conditional Denoising Diffusion Probabilistic Model for Point Cloud Upsampling. This paper was published on CVPR by Wentao Chu and colleagues from Nanjing University of Science and Technology and Shanghai AI Laboratory. The abstract introduces the concept of point cloud upsampling, PCU, which enhances the representation of raw point clouds, thereby improving performance in tasks like classification and reconstruction. Unlike existing methods that focus on feature extraction and upsampling module design, the authors propose a novel approach that models the gradient of data distribution directly from dense point clouds. This approach, named PDM, is a conditional denoising diffusion probability model that treats sparse point clouds as a condition and iteratively learns the transformation between dense point clouds and noise. PDM also aligns with a dual mapping paradigm to enhance feature discernment. The model enables the learning of complex geometry details without needing additional upsampling modules and can generate high-quality, arbitrary scale point clouds by leveraging scale knowledge during training. Experimental results show that PUDM outperforms existing methods in terms of chamfer distance, CD, and Hausdorff distance, HD, achieving state-of-the-art performance. Point clouds, despite their widespread use in 3D tasks, face significant challenges such as sparsity, noise, and non-uniformity. Existing methods like PUNet have made strides but suffer from indirect coordinate prediction and feature non-dominance. In contrast, PUDM, based on conditional DDPM, directly models dense point cloud features, employs a dual mapping paradigm, and can generate high-fidelity point clouds at arbitrary scales, addressing these limitations effectively. Figure 1 compares the performance of various point cloud upsampling methods. It highlights that while existing methods achieve satisfactory results for sparse point clouds with clear geometric structures, they struggle with those containing fuzzy details. In contrast, our method demonstrates close proximity to the ground truth, indicating superior performance in handling both clear and fuzzy geometric details. The integration of deep learning with 3D data has led to significant advancements, with networks like PointNet, PointNet++, and DGCNN enabling feature learning from point clouds. PUNet was the first to apply deep neural networks to point cloud upsampling, followed by methods like MPU and PUGN achieving more significant results. PUEVA introduced arbitrary upsampling rates, while PUGO and NEPS focused on sampling within a 2D space for higher quality. GradPU transformed upsampling into a coordinate approximation task. Most methods predict dense point cloud coordinates from sparse features, but struggle with complex geometry and noise. This paper introduces conditional DDPM for point cloud upsampling, overcoming issues like computational complexity and time overhead seen in previous DDPM applications for point cloud generation and completion. The Denoising Diffusion Probabilistic Model, DDPM, establishes a transformation relationship between a dense point cloud X and an implicit variable Z through two Markov chains. The forward process gradually adds noise to X, while the reverse process slowly removes noise from Z. The training objective under specific conditions is defined by a loss function L, theta, which involves the gradient of the data distribution. Despite its advantages, DDPM has limitations such as weak feature perception in point cloud conditional networks, difficulty in handling arbitrary scales during inference, and a high training cost. The methodology of PUDM involves two key components: dual mapping and rate modeling. In the dual mapping paradigm, the authors provide a formal exposition of the concept and demonstrate how PUDM aligns with these principles, particularly focusing on the role of the conditional network in establishing a one-to-one point-wise mapping. For rate modeling, the approach involves adding a rate label R to each sample pair, which is parameterized using an embedding layer. This addition to the reverse process of DDPM significantly improves the generation quality of unseen scale point clouds. The network architecture of PUDM consists of three crucial components: the conditional network, CNet, the noise network, NNet, and the transfer module, TM. These components facilitate information exchange and enhance semantic understanding, contributing to the overall effectiveness of the model. Figure 2 illustrates the overall framework of PUDM, which consists of two main branches, the NNet, noise network, and the CNet, conditional network. Both networks are designed to establish a one-to-one pointwise mapping between the input and output using mean-squared error loss. This ensures precise and accurate point cloud upsampling. The two networks engage in information exchange through a transfer module, TM, which facilitates bidirectional interaction and enhances the overall performance of the model. Additionally, the rate prompt is provided to exploit the prior knowledge of the scale between sparse point clouds and dense point clouds, ensuring that the upsampling process is both efficient and effective. The experiments utilize two public benchmarks, PUGIN and PU1K, for evaluation. These datasets are processed using Poisson disk sampling to generate uniform patches for training. Each patch contains 256 points, while the corresponding ground truth has 1024 points. The input sparse point clouds consist of 2048 points and are upsampled to 2048 times our points via evaluated methods. The evaluation metrics employed include chamfer distance, CD, Hausdorff distance, HD, and point-to-surface distance, P2F, following established practices in the field. Figure 3 presents the visualization results of 4 times upsampling on PUGIN. Our method demonstrates a notable reduction in outliers compared to other methods. It effectively captures and reproduces intricate geometric details from the ground truth, such as the holes on the casting. This level of detail preservation is crucial for applications requiring high fidelity in point cloud upsampling. Figure 4 presents a comparison between GradPU and our method at large rates on the PUGIN dataset. The primary focus is on the quality of the surfaces generated by each method. Our method consistently demonstrates superior performance in generating more uniform and smoother surfaces. These results were obtained using an NVIDIA 3090 GPU, highlighting the computational efficiency and capability of our approach. The visual and quantitative differences in surface uniformity and smoothness between our method and GradPU are evident, underscoring the advancements made by our approach in point cloud upsampling tasks. Figure 5 presents the results of 4 times upsampling on the KITTI dataset. Our method demonstrates a significant improvement in generating more reasonable and uniform results, particularly on complex geometric structures. This enhancement is crucial for applications requiring high-fidelity point cloud data, such as autonomous driving and 3D modeling. The uniformity and detail consistency achieved by our method are key advantages over existing techniques, which often struggle with maintaining geometric integrity in complex scenes. Figure 6 presents the results of a 4 times scaling on the ScanNet dataset. The outcomes demonstrate a notable reduction in the occurrence of outliers, which are points that deviate significantly from the expected pattern. Simultaneously, the generated surfaces are more uniform and complete, indicating improved consistency and coverage. This enhancement is attributed to the implementation of the dual mapping paradigm, which augments the capability of perceiving point features within the PUDM, point-based unsupervised domain mapping, framework. The figure visually confirms the effectiveness of this approach by showcasing the more refined and accurate geometric structures produced. Figure 7 presents the visualization results of the CNet generating sparse point clouds on the PUGIN framework. This visualization effectively demonstrates that the CNet has been successfully trained and integrated into the PUGIN system. The results highlight the CNet's capability to produce accurate and sparse point cloud data, which is crucial for various applications in 3D modeling and computer vision. The successful integration of the CNet with PUGIN underscores the model's robustness and its potential for further advancements in point cloud generation technologies. Table 1 presents the results of 4 times and 16 times upsampling on the PUGIN dataset, demonstrating the substantial superiority of our method in terms of chamfer distance, CD, and Hausdorff distance, HD. Our method significantly reduces CD and HD, indicating superior geometric detail description compared to other methods. This is attributed to our method's ability to model the gradient of data distribution from dense point clouds, facilitating the direct approximation of geometric details from the ground truth. Consequently, our results exhibit higher accuracy in approximating geometric details, as evidenced by significantly reduced CD and HD values. Table 2 presents a comparative analysis between GradPU and our method at various rates on the Pugin dataset. The table highlights that our method, benefiting from rate modeling, continues to exhibit remarkable performance across different rates. Key metrics such as Hausdorff distance, HD, and chamfer distance, CD, demonstrate substantial advantages for our method over GradPU. This indicates that our approach effectively leverages rate modeling to maintain high performance, even when scaling the point cloud upsampling process. Table 3 presents the results of 4 times upsampling on the PU1K dataset, utilizing experimental results from the original paper. Our method demonstrates superior performance, outperforming other methods across nearly all evaluated metrics. This table highlights the effectiveness of our approach in handling upsampling tasks, providing a comprehensive comparison with existing techniques. Table 4 presents the results of 4 times upsampling under low-level Gaussian noise on the PUGN dataset. Our method demonstrates a significant advantage in noise robustness, outperforming other methods such as PUNet, MPU, PUGN, DisPU, PUEVA, PUGCN, NEPS, and GradPU. This superiority is evident across multiple noise levels, particularly at tau equals 0.01 and tau equals 0.02. The key performance metrics highlighted include Hausdorff distance, HD, point-to-feature distance, P2F, and chamfer distance, CD, where our method consistently achieves lower values, indicating better performance in capturing geometric details and reducing outliers. Table 5 presents the results of 4 times at high-level Gaussian noise on PUGN, comparing various methods including PUNet, MPU, PUGN, DisPU, PUEVA, PUGCN, NEPS, GradPU, and our method. The table highlights our method's superior robustness to noise, as evidenced by the lower values in the CD, chamfer distance, HD, Hausdorff distance, and P2F, point-to-face distance, metrics. Our method notably generates more reasonable and uniform results on complex geometric structures, demonstrating a more favorable upward trend for robustness to noise compared to other methods. Table 6 presents the results of applying 4 times high-level random noise to PUGN. Our method consistently outperforms other methods across all evaluated metrics, demonstrating superior robustness and effectiveness under noisy conditions. This table highlights the comparative performance of various methods, emphasizing the superior results achieved by our approach. Table 7 presents the results of point cloud classification, comparing low-resolution subsample point clouds with high-resolution original test point clouds. The metrics used are instance accuracy, IA, and class accuracy, CA. The results show that the method described in the paper achieves more reasonable, finer-grained, and closer to ground truth geometric structures, leading to a significant improvement in classification accuracy. Table 8 presents the results of an ablation study focusing on the dual mapping paradigm. The study evaluates the impact of different configurations on performance metrics such as chamfer distance, CD, Hausdorff distance, HD, and point-to-feature distance, P2F. The data clearly indicates that the construction of the dual mapping pattern significantly outperforms other configurations, achieving the lowest values in all 3 metrics. Specifically, with the dual mapping pattern, the CD is 0.131, HD is 1.220, and P2F is 1.912, demonstrating the effectiveness of this approach in enhancing point feature perception and overall performance. Table 9 presents an ablation study on the rate prior, demonstrating its significant impact on enhancing the quality of arbitrary scale sampling and point cloud generation. The study shows that without the rate prior, the overall performance notably decreases and exhibits significant fluctuations across different rates. In contrast, with the rate prior, the metrics for Hausdorff distance, HD, point-to-feature distance, P2F, and chamfer distance, CD, are consistently reduced, indicating a more stable and improved performance in point cloud generation. Table 10 presents an ablation study focusing on the transfer module, TM, within the context of a UNet architecture. The study compares the performance, and computational efficiency of using a single TM versus multiple TMs. The results indicate that while multiple TMs lead to a slight reduction in chamfer distance, CD, loss, the improvement is not substantial enough to justify the significant increase in computational cost. Specifically, the single TM configuration achieves a CD loss of 0.131, while the multiple TMs configuration achieves a slightly lower CD loss of 0.129. However, the computational cost, measured by the number of parameters, increases from 16.03 m in the single TM setup to 28.65 m in the multiple TM setup. This trade-off suggests that the single TM setup offers a more balanced approach, providing a reasonable performance improvement without an excessive computational burden. In this paper, the authors systematically analyze and identify the potential of DDPM as a promising model for PCU. They propose PUDM, which is based on conditional DDPM, enabling the direct utilization of dominant features to generate geometric details approximating the ground truth. The authors also address the limitations of applying DDPM to PCU, such as the absence of efficient prior knowledge for the conditional network and fixed-scale object modeling, and propose corresponding solutions including a dual mapping paradigm and rate modeling. Additionally, they provide a straightforward explanation regarding the robustness to noise for PUDM observed in experiments. Thank you for watching.